My motto is never use an elevator for elevation. I've got to keep in good shape, as you can see. But I have to admit that age is creeping on, so I have to pause for a breath every now and then. A short stoppage, you might say. But of course, if I trained all day, every day, I wouldn't need a break. But with machines, the stoppages are more varied, both in frequency and how they happen. So is it really possible to achieve zero stoppages? Of course it is. Anything's possible. I'll show you a few steps to take.
On this production line, in order to be able to understand the actual conditions of short stoppages more clearly, check sheets are prepared for each piece of equipment. They are located along with the production control sheets in an accessible place, so that operators can fill in the sheet whenever a short stoppage occurs. The check sheets are totaled every day, and the data is kept for analysis when improvements are planned. As you can see, there is space on the production control sheet to make Pareto graphs. The data concerning the causes of short stoppages is shown on the Pareto graph in a way that can be easily understood. By drawing a graph like this, you can show important items which will help to get rid of short stoppages on the production line as a whole. The next step is to analyze the data theoretically. But what is theoretical analysis? Let's look at an example. This machine places processed parts onto items on the production line. However, here the parts provided by the parts feeder have got jammed on the chute. This used to be the most common cause of short stoppages. When this kind of stoppage occurs, operators tend to assume that there is something wrong with the angle of the blades on the part being processed. It's a fair assumption, as the blades do get tangled. However, if you think about this logically, the distance between each part is less than their diameter. This means that the parts are too close together, and that is the likely cause of the problem. Regardless of the shape of the blades, they would still get entangled. Like this, once you understand the situation theoretically, you can focus on the conditions which cause the problem. Generally speaking, you have to examine the situation from the viewpoint of materials, equipment, method, and people. In this example, 3 conditions are listed. Materials, meaning the shape of the parts. Equipment, meaning the shape of the chute. And method, meaning the means of supply. Once you've clearly determined the conditions involved, you can examine the factors corresponding to each condition in concrete terms. Now let's look at each factor in this example. First, materials, namely the shape of the part. Note the blades are curved. Second, equipment. There is an uneven connection between segments of the chute, creating a potential barrier. And third, method, the means of supply. There is pressure from other parts building up behind, and proper spacing is not maintained. Now we have isolated three factors, we can track down the real criminal in the case by comparing the situation with standard conditions where short stoppages do not occur. First, how about the shape of the blades? Yes, certainly the fact they are curved means there is a strong chance of getting tangled if they overlap each other. Second, how about the unevenness of the chute? No, it has no effect on whether or not the parts get tangled together. Third, how about the supply method? Yes, this is obviously the real problem. If the parts are pushed into each other, there is every chance they will get tangled. This is clearly the principal suspect. The method of analysing the phenomena of short stoppages by theoretical explanation of what is different from the standard situation is called PM analysis. It leads to the drawing up of improvement plans. It's done by carefully considering the four factors of machine, man, materials and mechanism. If we think of the way things should be and rethink the factors based on the basic concept, we can then produce countermeasures to all minor defects. In the example we've just seen, the operation was automatic, so they didn't have to focus on the man element, but concentrated on the other three M's, materials, machine and mechanism in that order. Once you've sorted out the problem points using theoretical analysis, you can move on to effect improvements of all defective points of the equipment. The next step is to go through the PDCA control cycle: plan, do, check, act. In the plan stage, you should list up the possible factors causing short stoppages and make the problem points clear, so that necessary countermeasures will become easier to formulate. In the do stage, you have to consider as many countermeasures as possible, select one and put it into action. In the check stage, you check your results to see whether the original plan has been achieved or not, and if there is still room for improvement. And then in the act stage, you implement further improvements as necessary. Working through the PDCA control cycle is one vital step on the road towards zero stoppages. The cycle is simple, but it's important to apply it deliberately in each situation until it becomes habitual. While you are involved in trying to improve defective points, it's important to grasp precisely how the equipment should be working. Remember that it's all too easy to be influenced by the ways of thinking and the methods which were used before you started working on improvements.
2,000 meters, 2001, 2002, well, time for a break. You've seen steps 1 and 2, which operators themselves have to implement. But steps 3 and 4 are coming up shortly, and can only be done in conjunction with the maintenance and design departments. A bit of teamwork. So, stay tuned to this video and get tuned up. 3, 4, 5.
How were conditions fixed in the first place for installation and processing of the parts and sub-assemblies we use every day? If you look at this in concrete terms, there are 4 basic conditions: position, method, angle, and vibration. To a large extent, these are based on past experience and technology. You often find they're not really in the best condition, and there may be a host of minor defects. In order to improve these minor defects, we have to rethink installation and processing conditions to try to get back to ideal conditions. This, of course, means ensuring that not even the smallest defect is overlooked. Let's look at an example. Here's a plan of a chute seen from above at a connection point. If vibration causes the connection to shift, the 2 sections no longer connect exactly. This is a clear recipe for trouble. Parts get jammed and you have a short stoppage to deal with. When the chute was designed originally, the plan seemed fine. However, once you start using the equipment, factors such as vibration can change the conditions sufficiently to cause a problem. In this case, the chute was redesigned to prevent lateral motion, which also seemed fine at the time. However, vertical vibration caused another bad connection and more short stoppages. Finally, ideal conditions were realized by a second improvement design. That was the end of short stoppages. Many people think there is no way to overcome the problem of short stoppages, but this example shows the value of examining the situation thoroughly and continuing to investigate ways to improve conditions until an ideal situation is achieved. The final step takes us back to the design stage. Full details about short stoppages should be fed back to the equipment designers and maintenance department engineers by the operators actually using the equipment. Based on this important information coming in from the factory floor, the project team can then set about the examination of all weak points as a guide to how to make future improvements. There are 2 methods of approach towards improvements. The first is examining the detection system. Are there any problems with the position or ability of the sensors or the whole system itself? Where are the weak design points? Improving detection systems means that defects are detected earlier and short stoppages needn't occur. The second method of approach is to improve the design of jigs and tools. Of course, you must understand the design weak points clearly before you can improve anything. First, you check each item to see if the alignment and positioning of the equipment or the shape of the jigs needs to be changed, and whether the jigs, tools and components of the machines are really useful or not in terms of materials used and functions. Then you can make a counterplan. This is not always an easy process and can't be done without a lot of repetition and trial and error, but it's important to keep at it. Here again are the 2 procedures for implementing improvement ideas. Improving weak design points via the detection system. and improving weak design points of jigs and tools. We've so far looked at 4 steps about counterplans to help us reach zero stoppages. This is known as corrective maintenance. It means maintenance activities which bring improvements by returning to the design stage. Based on the 4 steps of corrective maintenance, the short stoppage we looked at earlier with the parts feeder was successfully solved by installing a nozzle to blow air into the middle of the chute. This serves to separate the parts on the chute and keep the blades from getting tangled together. The result, zero stoppages. Finally, let's take a quick look at 2 successful examples of corrective maintenance. On this production line, parts supplied by 2 parts feeders are combined together and fixed on a workpiece. There are many factors here which could contribute to stoppages. Before improvement, if a short stoppage occurred on either of the parts feeders, then the whole production line came to a halt. Then sensors were installed. If a sensor detects a short stoppage, a lamp flashes and a buzzer sounds to inform the operators. A spare chute, parallel to the equipment, can be used to supply the combined parts while the fault is being fixed. This means that a short stoppage does not upset the whole production process. This equipment automatically does collet chucking to the functional part of the workpiece and screws it onto the product itself. However, the processed parts have a curved surface, so they are rather unstable. Before improvement, the part sometimes slipped sideways in the chuck and caused short stoppages. Analysis showed that the position of the part was not regular in the chuck. It was clear that if the chuck was at all worn inside, it could not hold the part in a stable position. In order to overcome this problem, a magnet was inserted. 2 metal plates were also added to the part of the chuck which suffers wear most to prevent malformation. The magnet fixes the position and the plates maintain the chuck walls. The result is accuracy every time and zero stoppages. Improvements which at first glance look quite simple are really the result of very careful checking of what is actually going on in the production process and determining deviations from the ideal. Short stoppages happen irregularly and unpredictably. Grasping the real situation behind the stoppage needs a lot of effort. The only way to achieve meaningful results is to work carefully through the steps and fully grasp the connection between actual conditions and the ideal conditions you want. Then you can really go about implementing improvements. Finally, let's review the 4 steps to zero stoppages. Step 1, analysis of short stoppage problems. Step 2, improvement of defective points. Step 3, examination of ideal conditions. And Step 4, improving weak design points.
3,776. Step by step. That's the secret. And I didn't stop once. Well, no, I didn't stop once. You see, the effort of making improvements is like going upstairs one by one. It's just like training your own body. Zero stoppages need a bit of effort. But I hope you can see it's worth doing. 4,000. Made it! Well, we've come all this way together. So, that's the end of our look at short stoppages. But why don't you take a short stoppage and enjoy the view from the roof? But I haven't got a head for heights, only for puzzles. So I'm back off down to my puzzle. Bye!